Right. So the last time, yeah, I was just being foolish because the thing is, I didn't realize that hinge forces um, can actually produce torques because till now I've always thought of the gyroscope as something like this. So you got this as the rod connecting to the central axis, and then you have this rotating wheel or something like that, or maybe a kind of a sphere or something like that, right? That was my gyroscope till now. Uh, right, and in that case, you would not have any torque because of hinge forces because take this as our origin. In that case, the r vector value for any force applied at the hinge, that is 0. So we don't have to worry about that, but now we do have to, because if this is not a single point where it's connected and instead it's like this, so this is connected like you know at a bunch of points, then there can be torques because of the hinge forces. So you might have some force application over here and then some other force application over here. So that's creating a torque about our origin. Does that make sense? Right. And our system is still the one that is connected to the axis, not including the axis itself. But okay, even if it did, it wouldn't change anything because, right. Yeah, I mean, it's inertia 0. So yeah. Now, that's good. And one case where you do have hinge forces creating torque is like you got a door. So a door which is connected at 2 points maybe, and at these 2 points you have forces pushing and pulling it, such that the torque to gravity is somehow cancelled, right? And you can take inspiration from that and say that okay, in this case as well, you might have hinge forces which are producing torque. Right, I should have understood that, but at that time I didn't actually think about it. Anyway, now we can do this thing. So a stationary platform P which can rotate freely. Oh, and also by the way, um, so I once again read this whole question and uh, I mean, I think that they didn't give us some vital information about this system because they gave us the angular velocity initially of this PV dash, right? So you get the thing, but in the final state, we don't know what's happening. So depending on how the angular velocity uh, of this sphere with respect to the platform is changing, you will have the angular velocity of the platform itself changing, right? Because yeah, consideration of angular momentum about the z-axis. We know that any hinge force, right, on this line, it cannot create an angular momentum so at all in the z direction, because r vector is always going to be along the z direction, and then it's a cross product, so it has to be perpendicular to that. So that momentum should be conserved and everything. So depending on what is the angular velocity in the z direction, you will have some angular velocity of this platform, right? We can do that. We can figure that out for this particular case because it's just 0, right? But there's the other angular velocity which we need to know to actually figure out torques and everything. So how do we do that? So yeah, like I searched everywhere for this, and turns out everywhere that I got, I mean, an actual answer for this, they took omega naught to be a constant. So right, I mean, this sphere is rotating with omega naught with this particular platform throughout the motion. It's not changing that magnitude. I don't know why that's a valid assumption to make, but that's what everyone is doing. So might as well do it this thing, right? So we can, I guess, assume that omega naught is gonna stay fixed, right? That value is just fixed. Okay, now let's do it. So what do we have? A stationary platform P rotating freely about a vertical axis, supports a motor M and balance weight N. Okay. Moment of inertia of the platform with the motor and the balance weight related to this axis is equal to I. And yeah, I mean, I did think about it that maybe there's something inside of the motor that is also having a part in the angular momentum. But then let's not give it all that much of thought because yeah, yeah, I don't think that's a good way to go. So yeah, I mean, we'll just think about this, right? Of course, maybe there is something inside M that's doing the thing, but in the final state where it's like fixed, that thing, its gears and everything, they will not rotate. So no angular momentum in the end, right? Okay. Yeah. Okay. Now let's do the thing. So moment of inertia of the platform with the motor at balanced weight related to this axis is I. Okay. So this and platform combined is just I about O dash. A light frame fixed to the motor's shaft with uniform sphere A, rotating freely with an angular velocity omega naught about the shaft dB dash, coinciding with the axis O dash right now, of course. The moment of inertia of the sphere related to the rotation axis is equal to I naught. Understandable. And because it's a sphere, it's I naught everywhere. Through every single diameter, it's going to be that. Okay. The work performed by the motor in turning the shaft dB dash through 90 degree and through 180 degrees. You want that. Using angular consideration, we can get what omega naught, what omega will be for this complete thing, right? Yeah, and think about it. If you didn't have the information that this guy's angular velocity is omega naught with respect to the platform, of course, you would never be able to figure out this energy, the final energy, because it could be anything along the horizontal direction, right? There's no way to figure that out. So you have to go with some assumption. Okay, and also you want moment of external forces which maintains the axis of the engine. Right, so it's not asking for the complete motion as it goes 90 degree. It just asks what happens at that point, right? Okay, no big deal. So initially, what is the angular momentum of this thing? This platform is not rotating. It's just that this thing is rotating, right? Oh, and finally, you also have 180 degrees. We'll just do the 90-degree case first, and then we'll go to, or you know what? For energy, let's just go for every single theta value because then you can just plug in 90 and 180 and get the thing done, right? Okay, what is LZ for any single theta value? So you got this, we'll just set up some variables. You got a platform, we'll just say it has anti-clockwise angular velocity. So from the top view, it's anti-clockwise. That will just be omega, and of this sphere will be omega dash, right? We know omega dash is just omega naught in the end. But yes, like with respect to this, you got this, and you can always do the superposition of angular velocity thing. Like I have a video for that. Go watch that if you want. All right. So you got this sphere. It has angular velocity omega naught in that direction. It's taking some angle theta with it. So its vertical component is just omega naught cosine theta, right? And then it's already having omega of this complete thing of the platform, right? So omega plus omega naught cosine theta. That's in the vertical direction for this thing. Okay. Um, yeah, right. And for the platform itself, it's just omega. So inertia of our, right. I mean, what I'm doing is just splitting it in this kind of thing. So one like that, and then yeah. And if you are still curious as to why I can break angular momentums like that, you should watch that inertia tensor video that I just uploaded. Because yeah, I mean, I figured out that something odd is going on over here. It's not planar object. It's not, yeah. So this is something that you need to know. Inertia tensors. Go figure that out. Go figure that out first, right? Watch that video, and you will understand why this can be done. So for axisymmetric cases, you can actually write this thing. You can write our angular momentum as angular momentum about x-axis, which is the inertia about x-axis times omega about x-axis plus angular momentum about y-axis, which is, you get the thing, inertia about y-axis, angular momentum about, sorry, angular velocity about y-axis, and so on, right? Okay, so in this case, the upward angular momentum is this guy, and also I omega, right? So this must be conserved. Okay, and this is actually what was the what was the thing initially? It was just omega is 0 and theta is also 0. So this will just be I naught omega naught. Cool. So you got our first equation. I mean, that's awesome. I naught. I mean, like I naught plus I is just kind of a constant. So I naught plus I omega, and you got 1 minus cosine theta. Awesome. So you got one equation. Okay. Now you know omega at every single theta value. Right. Next, what you want? You want the energy, because for A you have to do that thing. Okay. So the kinetic energy of the system and the potential energy doesn't change. It's just, yeah, the center of mass is just at that point. So what's the kinetic energy? Well, I mean, it has this component and this component. So Right. This is gonna be complicated. Uh, okay, so you got half I plus I. Okay, not like that. Half I naught omega y squared. Okay, omega x squared or whatever you want to call this axis, which is just omega plus omega naught. Right. This thing squared, of course. Oh, sorry, it should be omega naught cosine theta. Plus a half I omega naught sine. Okay, that thing squared because you got this component as well. And then you just have the platform. So half I, oh, it's I naught, sorry. Half I omega squared. Right, that's the energy. That's our kinetic energy, which is, just say 2 kinetic energy. What's that going to be? 2K is going to be equal to, so first of all, just take that I naught common. And then what you have, omega squared plus 2 omega omega naught cosine theta, and then you got omega naught squared cosine squared theta. But then that comes in and just becomes omega naught squared. Like vectors, of course, understandable, right? Because in the end, it's just these two combined. That vector, I don't have to explain that. And then it's just plus I omega squared. I Yeah, I mean this is kind of complicated, isn't it? Mm-hmm. You do know what omega is, so you can just put that in there and hopefully get something nice. Yeah, about that. Should I do that? I guess, because what other choice do we even have? Right? First of all, just simplify this a bit. So we can write this thing as 2I naught omega naught. And oh no, actually, you know what? No, that will just be problematic. Okay, now I have to put this there. Let's see. So first of all, just got I naught plus, yeah, we simplify this thing. I naught plus I omega square plus 2 omega I naught omega naught cosine theta plus I naught omega naught squared, and anything else? No. So just put omega as that thing, right? I naught omega naught upon I plus I. Yeah, those two i's, and square that's like I naught square omega naught square upon, yeah, one of them just cancels. You got this thing, and then you have this, so 1 minus cosine theta squared, and then just put that in there. So I naught omega naught upon I plus I naught, which, okay, that's kind of weird. It's gonna be squaring that, and okay, the same thing as this actually. So it's just I naught squared omega naught squared upon I naught plus I, and you got, oh, that's a 2 over there. Was that 2 there all the time? It was. Okay, and then you got 1 minus cosine theta times cosine theta, just c minus c squared, you can say. Okay, that's awesome. You know what? Just for convenience, we'll write it as 2c minus 2c squared. And then finally, you got this thing. So plus, oh, it's not half anymore. It's just this thing, I naught omega naught squared. Awesome. Yeah, right. That should, yeah, okay, that should actually work out. So first we'll simplify this thing. So it's I naught squared omega naught squared upon I naught plus I, and then this thing squared plus that, right? So like 1 minus 2c plus c squared times this thing, so you got minus c squared, and then 1 is there, and then minus 2c plus 2c, that's 1. Sorry. And whoa, look at that value. It's just sine squared. Isn't that right? That somehow happened. Yeah, that looks right, in fact. Okay, so that is sine square. Awesome. Then you got I naught omega naught square. This is our kinetic energy, or 2 times of that. So you got the value of k, or 2k, or whatever. Okay, cool. So, right, our k is basically just this thing, half I naught omega naught squared, because you can take some stuff out, and then you just got this thing, I naught sine square theta upon I naught plus I, because that's just pure numbers, I'm putting it inside, and then plus 1. Cool. Hopefully it's gonna work out. So at theta equal to 90 degree, this would be what? Oh, and first of all, you know what? Actually, let's write this down in more clean form. So you got omega, and you also got, yeah, we need this later on. Okay, whatever. We don't actually need this thing. So this is the thing, right? Okay, you got omega, and you also got k. So let's answer a in that case, because now we have expression for k. the work performed by the motor in turning the shaft EB dash through 90 degree, then in that case K will just become what? Hey, you know what? Let's actually figure out what delta K is, not K, because right, so like delta K, that will just be this thing minus initial one, but the initial energy was just half I naught omega naught square, because initially this platform was not moving and this was moving with omega naught. So this is our delta K. Awesome, is it? Yeah, it really is. Okay, actually simplify this thing even further. So it's like I naught squared omega naught squared sine squared theta upon 2 times of I naught plus I, that is our delta K. Yeah, that's better. So n of our delta K is just the work done. So the work done to turn by that angle is this thing. Now, the work performed by the motor in turning the shaft dv dash to 90 degree first of all. So just put theta equal to 90 degree. This is going to be I naught omega naught squared upon 2 times of I naught plus. Yeah, so just that thing. A. So 90 degree, it's this. Okay, and for 180 degrees. So in that case, sine theta will be 0. So okay, yeah, W is 0. And yes, I think that's a good thing. W is 0. Sure. Still looks weird actually. But somehow that's what the maths tells us. So I'm gonna go with it. At 180 degree, the work done is just 0. Okay, whatever. And then let's go for B. So the moment of external forces which maintains the axis of arrangement in the vertical position after the motor turns the shaft dB dash through 90 degrees. So yeah, okay, we can do that. It's going to be dl upon dt of the whole system. Right, and now it's like 90 degree, it's just omega naught in this direction for the sphere. Everything else just has a vertical angular velocity which is actually not changing with time. So you can ignore that. It's just this that we have to look for. And oh, actually we do need the angular velocity at, right, so what is omega going to be? Just, you know, the normal omega thing. So theta is what, by the way? 90 degree. This is going to be gone. Just I naught omega naught upon I naught plus I. Okay. The reason I'm doing this is because this is like omega naught r hat. So the time derivative of this thing is going to be omega naught times omega and then dr hat upon dt, which is the tangential directions like t hat, right? Isn't that obvious? Yeah, because like this vector is rotating along the platform. It's like fixed to the platform, if you will. Okay, that's awesome. So what is this value going to be? Just, you know, multiply this thing by omega naught. There you go, I naught omega naught squared upon I naught plus I. That's the torque, and it's along the t hat direction. So you know what? Actually, it's gonna put that. Yeah, I'm gonna put that. Who cares? Or you know, no, because they won't understand what t hat is, since you know my terminology. So B is done. Okay, I don't want that. Yeah, this is better. All right, next question. First of all, minimize some stuff because. Mhm. All right, 281. A horizontally oriented uniform rod AB of mass m equal to 1.4 kg. So mass is given as just 1.4. Length is 0.1 centimeters. Rotates freely about stationary. Still draw it out. So horizontally oriented. It's a rod AB about a vertical axis O dash passing through its end A. So this is the axis O dash. Fine. The point A is located at the middle of the axis OO dash. Okay. Whose length is L equal to 55 centimeters, just like L equal to 0.55. Okay. And at what angular velocity of the rod, the horizontal component of the force acting on the lower end of OO dash is equal to 0? What in this case, what is in this case the horizontal component of the force acting on the upper end of the axis? It's horizontal, then there's like gravity acting. Sure. I mean, I did say that this force cannot actually change the angular momentum of this complete thing. Sure, I did say that, and that's actually correct. No big deal with that. About this point, it cannot change. Um, right, but it's not like this anymore. Yeah, I mean, how do I explain this thing? Ah, right, it's hard to explain. Mm. We know it's going to be rotating like this. So omega is also going to be pointing outward. Where gravity is pointing in this direction, you have some forces pointing due to that, and there will be torques and whatnot. Oh, okay, okay. Now I remember what was happening. For the gyroscope, this point was actually a hinge point. That is, right, it was like at this point, this actually could move, if that makes sense. In this case, it's not possible. So, yes, this point is under extreme stress because it has to provide a torque, which is like, yeah. So, think about it. It's like if you actually made this out of steel or something, you would have a steel rod, and then attached to it is another rod, which is like much bigger because this is light and this is heavy, right? Yeah, and there is a bit of thickness, even though we think it's not there, it is there. And this, this kind of thing happening, so it's basically like a door. Yeah, it's just a very, uh, very, okay, a door with very, very short height and a very big width. Does that make sense? It is basically a door, if you will. And so there must be torques at this point on this thing, right? So I did say that there would be no torques, but that's for a gyroscope, not for this thing. For a gyroscope, yes, there's no torques because it's actually a single point where it's attached, right? If something like that was happening, it wouldn't be a gyroscope anymore. Does that make sense? Sure. And then you would actually have to consider the whole body as a single thing because, yeah, the thing would go like it just becomes complicated. So that's how it should be. Um, okay, and now we do have to do that. We have to consider the whole body, this whole frame, as a single thing, which is obvious. Rigid body, right? Yeah. So, you got the center of mass somewhere over here. So, with respect to, let's just say this point, or no, let's just say this point actually. So, with respect to this point, you have a torque because of this. Okay, maybe we should, because we just want the force on this, right? So, you take this as our reference point. So that you can figure out the torque because of this guy, and then you will have some force because of that and whatnot. Okay, that's supposedly better. Hmm. And then the net force is, of course, the centripetal force of the center of mass. Sure. Okay. It's weird. So torque is in clockwise sense. You want anti-clockwise torque. So you got forces in this direction, and also superposed with that forces in these directions, which is because of the centripetal force, right? If that happens, then you have this thing, right? Wow, this was weird. Okay, now they gave us M, L naught, and L. We have anything else? At what angle the velocity of the omega is okay, omega is what you have to figure out. Okay, horizontal component of the force acting on the lower end is equal to 0. Fine. There is that vertical force, of course, because gravity has to be opposed. But then those don't produce any torques because, yeah, that makes sense. Um, right. So this thing, it's like, okay, you got the gravity, which is mg, and then you got L naught upon 2. That's the torque, and that's just equal to. So we are taking this as our reference point. You got this as our r vector and cross with that, so you get the thing r with this is this, and then you have this force, so the net force pointing in that direction. Let's call this up and lower point. We don't want o dash or whatever. And with respect to up, this should be pointing, so the force on this should be pointing in this direction, I guess, because, but yeah, that should be the thing. Isn't it weird that it's actually pointing in this direction, although the centripetal force is actually supposed to be pointing in this direction? It is. Okay, whatever. It's just equal to whatever this force is. So that force times this length, which is just L. So F is just equal to mg L naught upon 2L. Now you can do this. So this is like F at L, and it's along this direction. And for this guy, just have F up is equal to. So if you take that as a reference point, then for the upward guy, just force is pointing in this direction. Yeah. So once again, pretty much the same thing, just that it's pointing in this direction. Wait, something's not right about this. Torque balance. Angular momentum is in that. Oh yeah. L equal to I omega. Oh, oh, that's a problem. If you took this as our point, it would be a planar. Oh god, no. I fell into this trick. Ah, I can't just say L equal to I omega. That is wrong. That's wrong because we are not in the plane of this rod anymore. Oh god. Right. So if you could say L equal to I omega, then that's good. Suddenly your torque is zero on this complete system. But now we're not on the system anymore. So what is this? Uh, yeah, well, so you could do this thing like center of mass, equivalent to off center of mass and about center of mass. About center of mass is not changing. Off center of mass, it is changing. Oh no. Like right now, it's pointing in this direction, and then after some point, if you point in that direction, it's not good. It's just not good. Okay, so don't take these as a reference frames. It's not so easy. You can't just do it like that. Man, I almost fell into their trap. You will have to take A as the reference point because in that case you can say L equal to I omega and torque equal to 0. Okay, now let's do it properly this time. So we'll just say this FL and we'll just say both of these are actually in this direction. So it's FL and this is FU and this is our A, whatever. So the torque, think about that. You want this to be anti-clockwise, right? So Fu times L naught, no, just L upon 2 minus FL L upon 2. When is that? It's not anti-clockwise, so negative mg L naught upon 2 is equal to 0. So Fu minus FL, or just Fu is equal to FL plus mg L naught upon L. All right, and what else was there? Oh yeah, so the combination Fu plus FL is just equal to centripetal force, which is m omega square r, so like m omega square, and r is just L naught upon 2. There we go. That should do the thing. Right, and what do you want? We want at what omega will the lower force, so FL, be 0. Right, if FL is 0, then yeah, I mean these two will be equal. So in that case, omega square is just equal to 2g upon L. So like at this omega it will happen, right? Because I guess so. But yeah, that should be working out. And there's like vertical forces, we don't care about those. So yep, that should do 2g upon L, sort of that thing. Cool. And at this point, what will our Fu be? So Fu is just this thing. We know that, right? So Fu is just mg times L naught upon L. That's our answer. Okay. So our answer is omega is equal to square root of 2g upon L. And the force on the upper one is just equal to mg L naught upon L. Of course. Well, yeah, next question. Oh, actually, we have to calculate first of all. Right. So, Fu not small u. Okay, square root of 2g upon L. Square root of 2 times of g is just 10 upon L is just 0.1. I think we might have messed up somewhere because was that the thing? Well, no, it was m omega square r. Yeah, it was the thing. It's just this thing. So 0.1 is going to be what? N squared 2. This is just equal to n squared 2. It's like 14.142 or whatever. right? So like 1.4142, of course, 14.142. And what is FU? So it's once again mg, which is 1.4 times 10 is 14. And then you got, what is this? Hey, I'm thinking, what if I just put 9.8 over there? So this would be like square root of 2 times of 9.8 upon 0 0.1, like 98. Wouldn't that just be 2 times of 7? 14? Yeah. So instead of this, just put 14 in exact figures. Although g is never exact, but whatever. Now, this thing, so m is just 1.4, times g is 9.8, times L naught is 0.1 upon L, which is 0.55. You gotta figure out what this thing is. Cool. Now, how do I proceed? Hmm. 14 upon 55 times 9.8, right? Yeah. Now what? So 9.8 times 14. Yeah, I don't see how we could escape this. We'll have to do it actually. So, 98, 14. 2, 3, carry on. 28, 3 is just 31. 0, 98. 2912. So 129.2 upon 55, which is like what? First we'll need 2, so minus 110, and then you got what? 9 and 1, so 0.2. Then you gotta put point, so now you got 192 as the whole thing, so 192, right? Okay, for which you would need 3, I think, because, right, so like 0.3, and then you got minus 15, 15 is 165, so this, and then 12 minus 7, and then okay, that's like 270. Now 5, yeah, 5, because that's going to be 275, so it's negative 5. That makes sense. Pretty small, right? Maybe not that small. Okay, we should actually go with 4. So we'll go with 4 in that case. So it's what, 220, like you got 50. So for that, yeah, you just cannot do it actually. Like 1, no, not possible. So like 2.34 is a good approximation. Yep, this is just 2.34, right? Yep. Next question. You got omega, you got Fu. Next is 282. So the middle of a uniform rod of mass m length L is rigidly fixed to a vertical axis so that the angle between the rod and the axis is equal to theta. Let me just first of all draw it because I don't want to see any figure. So middle of the uniform rod of mass m length L fixed to an axis O dash. So the angle between the rod and the angle, okay, axis is theta. So like this would be theta or whatever. The ends of the axis O dash are provided with bearings. So this is bearings. I don't know why they are doing that. Okay, the system rotates without friction with an angular velocity omega. You mean the whole thing? Okay. Find the magnitude and direction of the rod's angular momentum relative to the point C. So what's C? Oh, they didn't give us what C is. So you have to see the figure in that case. 1.71, which is I think up because this was 1.72. Come on. Oh god. Okay. So C is this. Oh, it's just that. Okay, fine. So C is this point. This is A. This is B. Let's copy down the whole thing. And these are bearings. Ah, okay. It's like just yeah. So that it can rotate about that. Understandable. What question was this? 282. Okay. 282. That's not 282. Um, the ends of the axis O dash are provided with bearings. The system rotates without friction. Then angular velocity omega. Okay, about O dash, I suppose. the magnitude and direction of rod's angular momentum, omega, okay, m, relative to the point C, as well as angular momentum with no rotation axis. What? Rotation axis? Oh, okay, I see what's happening. So when it said related to C, I think it meant as in like the point. So in the ground frame, right? And when it said related to the rotation axis, it's referring to the rotating frame of O dash or something like that, right? So they want us to find the magnitude and direction of the rod's angular momentum. And then they want us how much the modulus of vector m related to point C increases during half a turn. Half a turn? Oh, okay. When the rod O dash turns by half. Okay, fine. And the moment of external force N on the axis O dash in the process of rotation. Interesting. I do have your omega like this. We saw in the last question that centrifugal forces would just straighten out the rod, right? And gravity cannot do anything because, yeah. And just as we always say, this point is not a fixed point, right? I mean, this is not fixed with that in that configuration, right? Instead, there's a hinge, so it can rotate about this point or something, I think. Wait, what? Rigidly fixed to the vertical axis. Wait, are you serious? What do you mean by that? Rigidly fixed? It cannot rotate? Huh. That doesn't make any sense. You mean like this is a frame? But how? How does that even make sense? How can that make sense? But in the last question, it was not fixed. In the last question, it was also rigidly fixed. Well, okay, 1.71. Let's see. So that is over here. And which of these refers to 1.71? Not this one. Not. Oh, here. Once again, that's just rigidly fixed. Moment of centrifugal force. Wait. Huh? Okay, I mean, this thing, it didn't even actually matter whether or not this was fixed because that moment is going to be the same thing. But what does it mean when it says it's rigidly fixed? Is the rod fixed in that particular orientation? I don't think so. Or maybe it is. I don't see a hinge point or anything. How do you even know if it rotates or not? Is theta a constant? It's a variable. We don't know. Ah, so what do I have? Okay, if it's not fixed, then it will just become more complicated, right? Yes, gravity is not doing anything, but there's centrifugal force which is gonna, yeah, create a torque relative to this rotating frame. Mm-hmm. Wow, it's weird. Um, Angular momentum has to be conserved. Mm-hmm. I guess you could just say that, okay, and not necessarily. What if it's omega is actually constant? Who knows? Ah, this is kind of weird. I didn't know a single word could mess up everything. How do we interpret the rigidly fixed thing? Do we say that point C of this rod is just attached, so with a nail or something, then it can rotate, right? Okay, once again. 22. And it says omega vector. It doesn't actually, I mean, yeah, if it was not actually fixed. In that case, your omega vector would be a variable, and then it should be like omega naught vector initially, because it's gonna be a variable, right? Yeah, the torque. So okay, maybe not. But angular momentum sure is not a variable if we assume it's like rotating without any external torques. It is having external torques. Ah, so I think it is like actually rigid, and this is a frame and it cannot, you know, move like that. If that's the case, then it's actually much easier. It's so much easier than what I thought. Angular and direction of rod's angular momentum related to the point C, as well as angular momentum related to point related to the rotation axis. So our omega vector is in this direction for this complete rod, right? So like this rod. That can be broken in this direction and in that direction. If you saw the inertia tension video, which I think you should, you would know that like this doesn't actually matter, just this thing that matters. So, that's weird. The angular momentum is somehow in this direction. Okay, yeah, wow. So it's in this direction. Although this was pointing in this direction, it actually is in this direction. Uh, okay, so fine. It's in that direction, and in that case, you want to take a component that's substitute the vertical one. Or we just want the omega as a vector. Oh, okay, we know it's just pointing upwards. So the negative direction of the rod's angular momentum related to the point C. First, we'll do that. Right. Is this axis having any mass? They didn't give us anything, so we'll assume it's light. In that case, just this rod is what matters. So yeah, I mean you can break it like this: one in that direction and one in this direction, and whatever. You can actually break it at like two of these guys or something, or fold it. Who knows if that makes sense? And yeah, this is what happens. It's just ml squared upon 12. That's the inertia about this axis. That thing times omega, right? Okay, component of that, of course. Don't be so silly. Just omega cosine theta, because oh no, omega sine theta, because this is the thing that you look for. So omega sine theta, and yeah, that's in this direction. Other guy is 0. Okay, uh, fine. And now what? Well, yeah, I mean that's the thing. That's our magnitude. So a part of, and you also want the direction. So maybe set up a coordinate system to give the direction. Yeah, just give us the angle. Right, so it's what angle with the vertical axis is just 90 minus theta. Right, so it's 90 minus theta with the vertical axis. And that's a good enough, thing. So A is done, basically. A, ml squared upon 12. And then you got omega sine theta. And making 90 minus theta with vertical. Okay, let's take it. Next question. B. B is how much the modulus of the vector m related to point C increases during half a turn. Okay. Modulus of the vector m increases. Oh, okay. First of all, A, you also have to give it around about the rotation axis itself. Okay. Okay. Wait, what? What do you mean by that? About the rotation axis. Oh, okay. The component of this about the rotation axis. Okay, so like cosine of 90 minus theta once again. Yeah, yeah. The sine squared. Okay, cool. So A is this, and then about O dash is this thing. ml squared upon 12 omega sine square theta. All right, now we can go to B finally. How much the modulus of vector m relative to point C increases during half a turn doesn't change in the first place because it's actually like constant. If theta is a constant, this is actually constant, so this is 0. And C, Right. I mean, they're talking about the modulus of the vector m, not the vector m itself, and then the changes modulus. Okay. The moment of external force n acting on the axial O dash in the process of rotation. So look, the horizontal component of this angular momentum, right? So like ml squared upon 12 omega sine theta cosine theta. That guy is rotating about the r hat axis. Okay, it's pointing about the r hat axis, which is rotating by itself. So the time derivative of that thing will just have omega squared, and then you got tangential component, right? So that's in the tangential direction. Does that make sense? Okay, that's the net torque. So moment of external forces on the axis O dash. I mean, in the whole, like on the whole frame basically, because what other torque is there? Gravity, doesn't do anything. So yeah, this is the thing. That should be the thing. Okay, so C is also done. And it's along with the head direction, which I won't write because they don't understand anything. Let's go to 283. 283 is a top of mass something whose axis is tilted by an angle of 30 degrees to vertical. So, okay. Oh, wait. And by the way, top is an axisymmetric body, which means you can write L equal to Lx, sorry, Ix omega x plus, you get the thing, right? So watch that video. Oh, come on. How many times have I already referenced that video? At this point, you would have watched this already. Okay, a top of mass something, m is equal to 0.5. Axis tilted by an angle theta is equal to 30 degree. Fine. Moment of inertia of the top related to the symmetry axis. So I see, just call it like that. Related to the symmetry axis. Of course, it's gonna be what? 2 gram. What? What is this? Grams? No, I don't want that. 2 times 10 power negative 3 kg meter squared, right? The angular velocity of the rotation about the axis is equal to 350. Wait. About the which axis? The central axis, right? The IC thing. Okay, of course. So omega naught. We just call it omega naught. Was yeah 350. Okay, this is from the point of rest to the center of inertia of the rod. In the center of mass. Okay, center of mass is at this point. Fine. So small r is equal to 0.1 or L or whatever you want. Okay, find first the angular velocity of the top's precision, which I'll call it omega, and the magnitude and direction of the horizontal component of the reaction forces acting on the top at the point of rest. So the vertical force is just mg. You want the horizontal force, which is okay. It's because of friction. And well, yeah, we'll figure that out using the force analysis because yeah, and there's no other horizontal force because gravity is the only force. So just the centripetal force of the thing, of course. That's the thing. All right, let's do the thing. So stop figure, first of all, we got this top, whatever body it is, we don't know. We just say this top is like this. You got a spear and then some other stuff attached to it. We don't know what that is, but yeah, it's axisymmetric and whatever. And this is our axis. It's making angle 30 theta with the vertical, right? Or what? Vertical, of course. So it's making angle theta. This angle is theta. Okay. The mass is at distance L. So like center of mass is distance L from this point, and its angular velocity about this axis is given by omega equal to 350. Okay. So even though it like has another angular velocity which is along this direction, right? We'll assume that's actually a constant to solve, right? Because if it is a constant, then it would work out. I mean, our solution would be correct. In which case, why look for anything else if you already can describe what the physical condition is? So we'll ignore that because it doesn't change. And then similarly, this guy's vertical component doesn't change. And you got this as our, I think this is our theta. So just the sine theta component, that's the one changing. So omega naught, okay, L, no, you get the thing. I see omega naught. Let's call it I actually, because there's no other inertia really. So it's I, oh God, what's happening? I omega naught in sine theta. That's this guy along r hat, and you know the thing, just this times of omega. right? That's our torque along the t-hat direction, but along the t-hat direction, the actual torque is just because of gravity. So this is just equal to mg, and then the arm length is just L sine theta, right? Well, yeah, of course, that has to be the thing. So there we go, this cancels, and then we got this thing. So, right, what will be asking? Omega is what? So omega is equal to mgl upon I omega naught. And in fact, this works out even like for every single theta value. So just, think of it as a formula if you want to. Okay, that's awesome. And what was the B part? The magnitude and direction of horizontal component of the reaction force acting on the right is just m omega square r. Yeah, m omega square and r is just L sine theta because that's the distance of the center of mass from here. So m, this guy squared, like, oh god, this guy squared. I hate this. M squared G squared L squared on I squared omega naught squared. And then that has L once again. What? L cubed. Then you got sine theta. That's weird. M cubed L cubed G squared upon I squared omega naught squared sine theta. Hey, is this dimensionally correct or not? MgL is a torque upon I omega is angular momentum. Wait, what? Something's weird. But yeah, it has, units of per second, so it's actually correct. Although it's kind of weird. Whatever. That's the thing. So you got the force, the horizontal force, right? Awesome. Now just, put in values and get the thing. Right. So what is omega going to be? Uh, so mgl, which is, what is this, like 0.5 is 1 upon 2, and you got g, which I'll just say is 10. L is 0.1, which is 1 upon 10, and then you got upon I. I is just this thing, 2 times 10 power negative 3, and that times of omega naught, which is once again just 1 upon 2. Did I mess up somewhere? No. No. Omega naught is 350, sorry. I did mess up. Okay, it's 350. Cool. So this cancels just 1 upon, or you know what, just put that 10 power 3, yeah, second power negative at this point. So like 100 upon 4 times of 3, 35, sure, which is like 50 upon 70, so it's 5 upon 7. So 5 upon 7 is what omega is. Cool. So this value is just 5 upon 7 in SI units, I suppose. Now, we have to figure out what this thing is. This is so not good. Why even, put it like this? Right. Why do all of this calculation? You already know what omega is. It's just m omega squared, and then you got L sine theta. So, who cares? Now, you already know what omega is, so that's just perfect. Now, what's m? M is this thing, then omega is this, like 25 upon 49. And then you got L. L was just 1 upon 10, and then sine theta is 1 upon 2. Okay, awesome. This is approximately 1 upon 2, what did you say? Right? I mean, I know it's slightly more than that, but this thing is like slightly less than this. This would actually also be slightly more. Okay, I'm going in the wrong direction in that case. Um, it should be slightly less than that. Oh yeah, okay, this is slightly more than the actual thing, and this is slightly less than the actual thing. Does that make sense? So I would say it's like a good compromise. So 1 upon 2 times 1 upon 2 times 1 upon 10 times 1 upon 2. That almost was a wrap. Yeah, is that right? M omega squared, which is just 1 upon 2, and L, which was 1 upon 10, and then sine theta is 1 upon 2. Cool. H is 1 upon 80. That's the what? The force, or what? Uh, yeah, it was the force. It's just 1 upon 80 newtons. Interesting. This is just 1 upon 80 newtons. Next question. And first of all, let's submit these values actually. Next, 24. 24 is, what is this? A gyroscope, a uniform disc of it is something at the end of a rod of length something. Okay, the usual gyroscope is mounted on the floor of an elevator car going up with acceleration omega is equal to something. Okay, so pseudo force. The other end of the rod is hinged at the point O. The gyroscope proceeds with an angular velocity and is equal to 0.5 rps. Ah, I hate these units. Who even uses this thing? Neglecting the friction and mass of the rod, find the proper angular velocity of the disk. What? Sorry, neglecting the friction and mass of the rod, find the proper angular velocity of the disk. What do you mean by that? Proper angular velocity? You mean like the complete vector angular velocity? So it's proceeding at what? Oh, it's precision rate is given. So that angular velocity is given, and it also has this angular velocity. You want the proper. What does that even mean? What does the proper angular velocity actually mean? I would say just that angular velocity plus this angular velocity plus superposition. Does that make sense? So that should be the thing. Sure. For that, you actually need to figure out what that thing is, right? Okay. Okay. Let's do the thing. Once again, pretty much the same thing as that. Hey, you could think of this as a top if you want, right? Because we already got omega in terms of omega naught. So why not just use that? Right. I mean, L, you already know how that's working. It's the center of mass. You will get that thing. Then MGL. So, yeah. And I omega naught, whatnot. I guess it's a good deal. So now you know what omega is in terms of that. So omega naught is just equal to MGL upon I omega. That's easy as, yeah. So you just got omega naught. Perfect. And now you can just figure out what the proper angular velocity is. Isn't that awesome? So what do you want? Just that, nothing else. Wow, that's seriously nothing else. Okay, okay, as you wish. So it is MGL, which is well, just leave it like that. We don't know what that is right now. We'll not put values. Okay, upon I omega. So inertia of this thing about the central axis, which is mr squared upon 2. No big deal. So mr squared upon 2, and then you got omega. So some stuff cancels just like 2gl upon omega r squared. That's what omega naught is. Is this the proper angular velocity or like omega naught vector plus omega vector the proper angular velocity? I would say the other one is because what's so proper about this? It just I don't know. Okay, that works out. So let's figure this thing. Uh, okay, it's gonna be what 2 times of g is just 10. L is 0.1 upon omega. If you convert this, oh god, 0.5 rotations per second, 0.5 times 2 pi per second, which is pi radians per second. So pi, and then you got r squared. Why are you putting me with this kind of troublesome thing? What is r squared? What is r? It's 5 centimeters. Why? 5 times 10 power negative 2 squared. 25 times 10 power negative 4. Isn't that just perfect? Wow. So 2 times 10 power 4 upon pi times 25. How does that make sense? Do they really want us to calculate this thing? Why is this in rotations per second? It's not even. Uh, oh, okay, okay. G is not 10. It is 12. Sorry. So this should not be this. It's like 1.2 times this thing, right? It's just 12 times 0.1. So it's gonna be 10 power 3 in that case. And then 2 times 12 is just 24. Okay, I guess. So this is the thing, right? That's what our omega naught is. And then you want omega naught vector plus omega vector, which is maybe one of them is very big. In that case, there's no need for the other one. Awesome. Of course, of course. Okay, we'll just figure out what these values actually are. And once again, omega was just pi. Okay. Trying to figure out what this thing is. Okay, I mean, okay, that's obvious that this thing is so much more bigger than this. But still, we'll do it. 24 times 4 is just 8, and then you got 16, which is like 96. 96 upon pi times 10, so like 960, is that right? Of course. 960 upon pi versus pi, I would say it's like much bigger than pi, because 960 is much bigger than 10, which is already bigger than pi squared, right? Isn't that a correct statement? Is this correct or not? To an extent, it is. So yeah, it's not much different from the perpendicular velocity in any case. Just put that as the thing. That's our answer. Cool. Or okay, maybe that 960 upon pi was actually better. So 960 upon pi. Next question. 280 what? 5. A top of mass something, moment of inertia related to its own axis I. Okay, spins with angular velocity omega. Its point of rest is located in, what is this thing? M equal to 1. Inertia is, why are they putting it in gram meter square? Okay, omega is 310. Finally, radians per second, not rotations per second. Its point of rest is located on a block which is shifted in a horizontal direction. Sorry, what? Point of rest is located on a block which is shifted. So it's a block. On top of that is the point of rest. So this is our whatever this is. Okay, which is shifted in the horizontal direction to constant acceleration. Okay. This is just really bad. Omega is equal to 1. Uh, not good. The distance between the point of rest and the center of inertia of the top equals L. Fine, L is just 0.1. Find the magnitude and direction of the angular velocity of precision omega dash. I don't get a good feeling about this. Omega is pointing in that direction. Yeah, I mean like G is pointing in some very weird direction. So what was the thing? Acceleration? 1 meter per second squared, right? So let's call it A actually, not W. A is just 1. And of course, we'll just assume G is 10 because it's in this direction, and then you have something in that direction, and then oh god, you can't even figure out the direction of this thing because it's so not good. So yeah, you could use this formula to get the thing, right? Because if you think about it, um, like yeah, you just got this surface, and then this point, it's still just a point. It's not anything different. So and then G is just some direction like that, and then this is our new down, quote unquote, down, right? Even though it's not actually the down direction, but whatever. So then with the vertical is making like theta, and then do the same derivation, and you'll get the same thing, right? I think so. So yeah, the magnitude is still the same, but the direction is like different. It is opposite to the G effective direction. Does that make sense? Okay. You didn't even give us coordinate axis, so how am I supposed to give you the direction with the angle with the vertical thing? Uh, it's not good. It's just not good, you know. Oh God. I get it, but it's just so not good. Fine. So you got omega. What's the formula? This thing, just put that in there and get something. And yeah, in this direction. So opposed to G effective. Uh, what's the angle? So this thing is 1. This thing is 10 or 9.8. I'm gonna say 10. So this is 10. This thing is 1. This angle theta is just tan inverse of 0.1. There we go. We say approximately 0.1. Wouldn't you say, because this is like a small number? Nah, don't go into all that stuff. This is good enough. So tan inverse of 0.1. Maybe 1 upon 10 can be written some other way. 1 plus 9. 9 is like 3 times 3. Doesn't make sense. Maybe something minus something is not the way, or whatever. So tan inverse of 0.1. Theta is just tan inverse of 0.1. You already figured that out. That's our direction. And we need the magnitude. Just do like that. mgl upon I naught omega. So m is just 1, g is 10, l is 0.1, so that's gone. And then upon 1 upon I, which is just this thing. And then omega, which is just 310. So this will be upon 1 to 4, and then that's 10.82, so 100 upon 124. That's our answer. So like divide by 5, I think. It's just 25 upon 331, right? Yeah. 25 upon 31, that's the, what was I doing? Omega. It's 25 upon 31. Omega dash, right? That's what you're saying? Yeah. In SI units, of course. It's like radius per second. And of course, we've got to do this thing. So to actually tell them what's going on. And yeah, that should be the thing. Now this is the point of rest. Next question. 286. A uniform sphere of mass something, radius something. Okay, mass is 5. Radius is 0.6. Oh, centimeters. Sorry. 6 times 10.82. With angular velocity 1250. Why is that a thing? About a horizontal axis passing through its center and fixed to the rotation, to the what? The mounting base. Rotates in velocity about a horizontal axis passing through its center and fixed to the mounting base by means of bearings. Okay. Distance between the bearings equals L equal to 15 centimeter. Horizontal X. Oh. Okay. It's the gyroscope, just a different version of it. Right? It's the gyroscope that you usually see. Yeah. Just not a disc, but a whole sphere. Distance between the bearing equals 15 centimeter. What bearings? Wait, what? Maybe that's not exactly what's happening. You are saying it's on a horizontal axis and fixed on sorry, fixed on the mounting base by the means of bearings. That's what I did, right? This is between the bearings. It's like 2 of them. Oh, so maybe like this thing. Okay, there are 2 of it. It's not a gyroscope anymore. Yeah, it's L equal to 15 centimeters. So this thing is L. Cool. 15 centimeters is like 15 times 10.82. The base is set in rotation about a vertical, what? Vertical axis with an angular velocity omega dash equal to 5 radians per second. So omega dash is 5. Okay. Find the modulus and direction of the gyroscopic forces. Look, it's just getting very complicated. What's going on exactly? Oh, so it's already rotating with some kind of omega. So like that's just omega naught basically. Omega naught is in this direction, and then you've got omega dash. That's just omega in fact. So okay, we should use omega dash because not to get confused. So it's just, yeah, doing that. Find the modulus and direction of the gyroscopic forces. That is the, but that's just torque that we can calculate. The forces by themselves. Oh, okay, this thing. These two are putting forces. That's what's going on, right? Yeah, well, they are putting vertical forces, sure, and they're also putting our dl upon dt is at a tangential direction, so Okay. I understand what's happening. They can't be putting they can't be putting horizontal forces because that would create torques which are in the vertical direction. So that's just unnecessary and not required. Okay, both mean the same thing. Unnecessary and also harmful because we don't want any vertical torques. Our torque is just in that direction. Hey, how do you figure out whether or not these two like and then of course like it's rotating, so this is not right. The forces must be equal and opposite because this whole thing's center of mass is not moving, I assume. So they are just equal opposite, and then in that case, they must be completely vertical. They can't have horizontal components because that would just mess up everything. So they are vertical, and oh, there's gravity as well. So like put those things in there as well. So other than gravity, so the components that yeah cancel gravity. Other than that, those are vertical forces. Does that make sense? Okay. So other than that, those are like equal and opposite. So you could think of it like this: you already got half of gravity force on like W upon two, so the weight upon two, and then with that you're also superposing more forces like F, and then this is negative F, right? So these F and negative F, like they can have any kind of direction, just that these are like equal opposite. That's all that we have to do. And yeah, so right, like by force analysis, it should be representable like this. And then just do torque analysis, and you will see that, oh, okay, these should be completely vertical. And there you go. So you just have to figure out what these gyroscopic forces are. Isn't that right? Yeah, I think so. These F values are just the gyroscopic forces and not the F plus W upon 2 and F minus W upon 2 things. What are they? These must be the gyroscopic forces. The other thing is just because of weight, nothing else. So let's figure those out. Like F times of L upon 2 because of one of these, but then F times of L because of both of them. So F times of L, that's the torque, which is just equal to, well, it's just I omega naught times omega dash. I don't like this, but whatever. And yeah, that's actually the thing. So we already got the thing. We got inertia using 2/5 of mr squared. It's a solid cylinder, right? Sorry, a solid sphere, right? So 2/5 of mr squared. And then you got omega and omega naught. Of course, just put everything in there. So FL is just equal to 2/5 mr squared omega naught omega dash. You just need to figure out what F is, which is like 2 mr squared omega naught omega dash upon 5L. Now just put in values and get the thing done. So 2 times what's the mass, which is 5 times r squared. So 6 times, okay, 36 times 10^4. Omega naught, which is 1250. Omega dash, which is 5 upon 5L. What is L? L is, by the way, just 15 times 0.82. Perfect. Let's calculate now. This cancels. You don't want that. Actually, you know what? No. Cancel this because that's going to be 10. And 10 times this is 10.3, 10.3, and then you got 10.82, but we'll leave that out for later. You got 36, and then you got like 2. Oh, wow. 1250. You can just make that 10 disappear by doing this thing. So that's perfect. Upon 15, is that right? Yeah, so this cancels. Just get this thing like 1 to 5 upon that. It's going to be what? 36 times 25 upon 3, which is like 12 times of 25, which is like 60 times 5, which is 300. So 300 is the value. That's the gyroscopic forces or whatever you want to call it. So F equal to 300 vertical or downward or whatever. Newtons. Wow, that's weird because like that's a lot of force, isn't it? It sure is, actually. Did I do this correctly or not? I was going to doubt it. No, it must have been correct. So there we go. Wow. Wow. It's 300. Like, how? I get how it's just 300 because 12 times of 25, but still. So it's 300 newtons. Yeah, those are the gyroscopic forces. Can't talk today. 287. A cylindrical disk of gyroscope. What's happening? My mouse is not working. A cylindrical disk of a gyroscope. Okay, of mass something. Mass is 15 kgs. Radius is 5 times 10 power 82. Angular velocity 330. Okay. The disk between the bearing of L equal to 15 times 10 power 82. And phi m. I know I don't even understand what's going on, but huh? Okay, I don't want this right now. Okay, what was this thing? Phi m. 20 days. 20 degree. Fine. Now let's read the thing. A cylindrical disk of a gyroscope of mass and radius spins with an angular velocity. Okay. Wait, what? The distance between the bearings in which the axle of the disk is mounted. Oh, so it's like the last case, just slightly different. Because now it's not a sphere, it's a disk. Huh, not a big deal at all. Right, that's L. Okay. The axle is forced to oscillate about. I should have written down the formula last time. And now I have to do it all of it once again. Oh, that's. Hey, no need for that. Because. Oh, okay. Let's not. Uh, okay, the axle is forced to oscillate about a horizontal axis with a time period t. What axle? Oh, this thing. Horizontal axis. Something's weird about this. What horizontal axis? Maybe they should have a vertical axis because how can this thing? The axle of the disk is mounted. Time period is given. Amplitude is given. What? What amplitude? What? It's so weird. Understand what's going on. What do you mean by this thing? Oscillate about a horizontal axis? Does anybody else understand what's going on? And I think it just spins with the same angular velocity everywhere, right? Okay. Another thing is it's like a horizontal axis about which is oscillating. So maybe like this. So right, it could be like you got this thing on which you have this disk. These are our bearings. Okay, right. So from these you got forces on this guy. Okay, and then this is the horizontal axis which is going. Does that make sense? It's too complicated, isn't it? Okay, and it's also looking what's axis with a time period something, an amplitude something. So like simple harmonic or what? Find the maximum value of gyroscopic forces exerted by the axle on the bearing. This is getting complicated. God. What is this? Omega, and then we got. Once again, you could do the same thing. I mean, you just got I naught omega naught, 10 times of omega. Maybe they are using some other notation. That's their omega. Well, right. So 1 upon time period is our omega. Does that make sense? Whatever. Just gonna do this thing. So I naught omega naught. Just gonna call it omega naught actually because just to stick with our notation. I naught omega naught omega. Um, that's our torque. In this case, it's in the tangential direction, right? It's like going, of course. So this is along this direction or whatever direction you want. Now, how can we produce this torque? it can be done if you got forces in like going in and out of the plane. In that case, that's gonna work. So F times of L, because that's the thing. F times of L is equal to this torque, right? Yeah. Of course, of course. What else? I'm missing something. There's the upward one, but we don't care about that really. Or do we? Well, maybe we do. Uh-oh. Right, because if it like precedes, or okay, it's not should precede, but if this angle changes at, I mean, it has a second derivative, then oh god, this angular momentum in the vertical direction is not constant anymore. And oh, I'm just getting what? No, that's not constant. And then you will have to, hmm, isn't this just horrible? And then to do this thing, you will have horizontal forces as well because, okay, you want the maximum of gyroscopic forces exerted by the axle on the bearing. Ah, shit. Oh god. We'll have to use the inertia tensor and whatnot because it's like, okay, you got this thing, you got omega in this direction, omega in that direction, and then you can just use, because it's like axisymmetric, so you can use that thing. So, right. Okay, it's not that bad actually. So the angular momentum is completely in this direction and this direction, nothing else, because there is no omega along the last axis, right? You can figure those out. Then this guy, it's just changing its directions. Because of that, you got a torque in this direction. And then this guy is like, it is changing its own magnitude. So you got something in that direction. And then finally the torque will be just, oh, I get what's going on. It's just so complicated. And then these forces will be in this direction and whatnot. Ah, get this. And then you do this. Oh yeah, you can just do the radial symmetry and then say that the final thing, the final torque that you will have, that's also equal to F times of L, right? Because for this kind of torque, I mean, yeah, just set up a new coordinate system and then, okay, no big deal, it can be done. It's just that I'm not sure what they want us to do. And is this oscillation harmonic oscillation or what is this? They gave us the amplitudes, but they didn't tell us what acceleration is. I mean, like, yeah, what is the maximum acceleration? And then also you actually need the omega for this thing and whatnot. Oof. So there's no other thing than like assuming it's simple harmonic oscillation. Because otherwise, how am I going to do this thing, right? How do I do this in any other way? So I guess that's the only way. Fine. So just figure out what that force's magnitude is, and then once you figure that out, good. Yeah. So like that, yeah, this force is in the vertical direction, and then you also got a horizontal force, which is so there's inertia about that axis. Oh god. Okay. Is that scary or what? Who would have thought? So yeah, look at that video of mine, inertia tensor. There I did this thing. I mean, inertia about an axis like this, that can be given as, so the inertia about this axis upon 2, right? Like you just got mr squared upon 2 already, but that thing upon 2 is like mr squared upon 4. Cool. But plus you also need the integration of dm times x squared. So right, like if r was very small, then this would basically be as if it's a rod. Does that make sense? And now we're just doing dmx squared, so it's still the same kind of geometry. Does that make sense? Then you just have ml squared upon 3 as that inertia. So you can in fact figure out, what the angular momentum is over here, and then just want, yeah, like dl upon dt, and that's the torque, and f times of l equal to that thing. So FL is just equal to this, and then you got omega, derivative is just alpha. So yeah, mr squared upon 2, okay, sorry, mr squared 4, ml squared upon 3 times alpha. It's really bad. And then I naught is of course just mr squared upon 2. So you got mr squared upon 2l times omega naught omega. This thing and this thing. So, okay, let's leave it like that. This is the vertical ones and this is the horizontal ones, right? And then combine them. Doesn't this look scary? It does. It really does, you know. Omega is a constant at least, so that's better. And you got omega and alpha, which you have to figure out. I mean, you could just actually figure out what these values are, and then you're good to go. Just plot omega and alpha. Something with that. I guess that's better, but I want a generalization. Why don't we just, put this as ix and iy right now and not care about anything. So yeah, like just ix upon L or something. What was the thing? F times L equal to, yeah. And F horizontal is just iy alpha upon L. Cool. We will figure those out later. Now, just do the thing. So like, if it's a simple harmonic motion, then omega is like cosine something. Okay, I get this thing. So first of all, just have to do the magnitude. So F total, I mean the magnitude of that thing, it is gonna be what? So yeah, like you got 1 upon L. That's the only common thing you could get. 1 upon L square root of ix omega naught omega square, and then you got iy alpha square. Oh god, it's getting crazy now. So, oh, and now it's going to be another set of omega and stuff because this is doing simple harmonic motion. Oh, I just hate this. Does anybody else hate this? 'Cause I do. Think. How do we maximize this? I have no idea. Because they want us the maximum. If they told us like the maximum horizontal force or the maximum vertical force, this would have been perfect. But they want the maximum gyroscopic forces. So, huh? Or maybe this one is not gyroscopic force. Is that the thing? Is this not a gyroscopic force? Because it, okay, then you might as well just put the mg value in the gyroscopic force. But we don't. So maybe we should not include this as well. It's just a notation difference, nothing else. There is this force and there's that force. What's the big deal about it? Which of these is gyroscopic? Who cares? But whatever, let's not include that because it's just getting too complicated. And I think they would not want this to be that complicated. So I think that's what they want us to find, right? And what's the maximum value of omega? Well, yeah, that's the question. Take out the amplitude, and then from that you want to figure out, and also the time period actually, right? So amplitude is given, time period is given, and now you want to figure out this thing. Okay. So suppose the retardation constant, okay, like the restoring force constant, which is k. So what I'm saying is like alpha is equal to negative k theta for that oscillation, right? Yeah, if that happens, um, right, in that case, the maximum omega that will be at the central point. And how do you get this? It's just half the x was like half k phi squared. Is that phi? I think so. Half k phi squared. This is equal to half. It's so weird. Now, what's this going to be? That's like supposed to be mv squared actually. Now, how do I? Yeah, what do I put there? Then what's k by the way? Oh, we can actually figure out k using t, right? So our time period. So like square root of k is omega, which is okay, that other omega, which is like 2 pi upon t. So 2 pi upon t is equal to square root of k. K is just 4 pi squared upon t squared. Okay, that's at least a bit better. Uh, right, and that is equal to half. Okay, now what's the kinetic, I mean the equivalent of kinetic energy in this case. I don't know. Yeah, I don't know. Uh, Something's weird. Oh yeah, I think we should actually write like this: d omega squared, okay, like omega d omega what of d omega squared upon d theta is just equal to negative k theta and whatever. So like d omega squared is just equal to like negative k d theta squared. Maybe that's a better thing to do. So the change in that is like fine. So like k, and then you got phi square. That's equal to the change in omega squares. Initially just zero, finally it's just something. So it's just omega squared. That's all we care about. Perfect, I would say. Yeah. So we don't need this in the end. It's just omega squared. Wow. Isn't that good? It sure is. So you got the thing. Uh, oh, come on. Okay. So you got what maximum should be. Omega max is just equal to 2 pi upon t. I just put m times phi, right? Just put that in there and you get the maximum force. So it's Ix omega naught upon L, and that times omega, which is this thing. So 2 pi upon t phi max. Cool. So much analysis, and in the end, I just had to discard this force. Wow. Because there was no other way. How would I have done this? Nope, no other way. And of course, we know what Ix is. It's just mr squared upon 2. So mr squared omega naught upon, and then it's 2, so just got pi upon t phi max. Right, and then the 2 cancels, right? You got L. Yeah, that's our final answer. Perfect. Now, just put in values. So m equal to 15. R is this thing, 5 times 10 into 2 is like 25 times 4. Omega naught is 330. Pi 3.14 is good enough. Like 22.7 if I want. I just leave it like that. Pi, yeah, who cares? Phi is 20 degrees. I don't want it to degrees, I want in radians. That's just equal to 20 upon 20.180 of pi, right? Which is like 1 upon 9 pi. Oh, that's awesome. Because pi square is just 10, approximately, that is. I think so, yeah. You got L and T. So T is just 1, L is 3 times 1.82. Hey, R was also that, right? Why is it 5 times 1.82? Whatever. And M was 15. Okay, that's fine. There's 15 over there. Cool. Cancels. 10 power negative 2. 10 power negative 1. It's got like 1 upon 90 because of that thing. Then you got times 25, then 33, then pi squared. So pi squared is approximately 10. This cancels. This will cancel that, like just 25 times 11 upon 3. So 275 upon 3, which is something like 90. Okay, 91 point something. 91 point. So you want what, 86, and then so on. 6, 7. I guess 92 is a good enough approximation. So like 92. 92 is this value. SI units. What was this thing? Force. So newtons. Next question. And we don't want all of this. 288, which is a ship moves with velocity something kilometer per hour. Oh god, I don't want that. Kilometer per hour. It's like 1000 upon 3600, which is like 10 upon 36, which is 5 upon, and 10 5, yeah, 10 upon 36 is a good enough thing. So V is just 10 meter per second. Okay, along an arc of circular, okay, a circular arc of radius 200 meters. So R is 200. Find the moment of gyroscopic forces exerted on the bearing of the shaft What? The bearing by the shaft with the flywheel whose moment of inertia related to its rotation axis is I equal to, okay, I is equal to, what is this, 10 power 3 or, yeah, that's better, 3800 if you want. That's better, 3800. Okay, and whose rotation velocity is rotation per minute. What's this? Rotation per minute. Wow. Do they have any idea how difficult they are making this for me? Can't they just put it as sensible people? I mean, 10 pi. Just write 10 pi. What's the big deal? Why did you write 300 RPM? Omega is just 10 pi. I get it. That's what I would get in the real life scenario. But why? Why right now? The rotation axis is oriented along the length of the ship. Okay. So you got a ship. Then this is rotating about this point. Then you got an axis which is on. Okay, fine. About that axis, you have a flywheel. Okay, so you got something rotating. Okay, fine. Rotation velocity, this is the length of the ship. So this is right. This guy's L is in this direction, and then you also have this L like that. But whatever. Yeah, this vertical L, we don't care about that. And you want the, so just the flywheel. Consider just the flywheel as a system. You want find the moment of gyroscopic forces exerted on the bearing by the shaft. Okay, so like opposite of that torque. Fine, fine, fine. So what's the torque by the bearings on the shaft? First of all, figure that out. That's just the net torque on this thing, right? So like that's the net torque about the center of mass. Well, yeah, which is also the net torque about this guy because no other force is there, is it? When the centripetal force doesn't really matter because, right, it doesn't matter. So that's that force which is it is pointing upward or something. Okay, it's going like this. So del upon dt is like, as long as dt had direction, so that of that is like negative r hat. So it's along this direction that you will have the power torque force. So because of that, these forces, right, they produce the torque like this. Now the opposite of that is what we want. So our torque, like the one we put in answer, is actually in this direction, whatever. And this torque is of course equal to like L omega naught times omega. Sorry, I what am I doing? I omega naught times omega, right? Where omega is like how fast like it moves around this point, and omega naught is actually this guy's own omega. Does that make sense? Okay, so we know what I is. We know what was this omega, by the way? Oh, okay. The omega thing, actually you can figure that out. And omega naught is just 10 pi. Cool. Right, right. That's it. That's the thing. So just figure out that torque. Huh? It's so easy. And you also want the direction. No, you don't. Any coordinate system, nothing. So just put the magnitude. Wow. We don't have to worry at all. Cool. Just I omega naught omega. You already know what I is. Yeah. So I is just this thing. Yeah, still I omega naught. And then omega for that V upon R is good. So 3800 times omega naught is just 10 pi times V, which is 10 upon R, which is 200. That's the thing, right? That's our torque. Cool. In what units? Nothing is given. Fine. This cancels. Just got 100 over there. So 3800 upon 2, just 1900 pi. Huh, easy as that. Pi. Yep, that's the thing. Do I need to elaborate further? Maybe I should. Okay, just 19 times 3.1. Yeah, what's the big deal? Just 314.16. Like, yeah, okay. And that terms of 19, I think. Okay, let's do it. So, 5 carried on, 9, 60, 14, 1 carried on. 1, then you got 36, 36, 7, so 3 carried on, 3 times just turn 2, 1 carried on. And then you got 27, and 1 is just 28. Then, it's just 0, and then it's 1, so copy it down, 6, 1, 4, 1, 3, 6, 9, and 5. So 5, 9, 6, approximately 6, 0, 0, 0. Okay, maybe not. I really want to approximate so bad, right? Who cares? 6,000. 6,000 is the thing. Round figure? Yeah. 6,000 newtons. Next question. Is this newtons or what? No, it's not. Sorry, it's Newton meters in that case. Or like joules. I don't like joules because those don't give me the feeling. That's a torque. So 289. Last question. Locomotive is propelled by a turbine whose axle is parallel to the axis of the wheels. Turbine. Sorry, what? Axle is parallel to the axis of the wheels. But how is that? That's a weird thing. Propelled by a turbine. But this guy's axle is parallel to the axis of wheels. So, huh? Okay, the turbine's rotation direction coincides with that of the wheels. Okay. Moment of inertia of the turbine rotor related to its own axis is equal to this thing. Find the additional force exerted by the gyroscopic forces on the rails when the locomotive moves along a circle of radius something. Find the additional force by the gyroscopic forces on the rails. What rails? Of the turbine. That's what you're saying. The locomotive moves along a circle with radius something. Isn't that the same thing as the last question? No, it's not. It's slightly different. Very slightly different. In that case, the axis was the thing. Now, in this case, the bearings are what we... Wait, something's weird. What's on axis? The rails. Ugh. Look, I don't know what exactly going on. So, it's propelled by a turbine. What? But then this turbine is rotating with the same direction as the wheels. So how does that actually propel the... Huh? Yeah, how does that happen? It's a locomotive. So it's like a train or something. So if it's a train, turbines, what? Whatever, just some kind of rotating body. We don't need to go into all the details. The moment of inertia of the turbine rotor related to its own axis is equal to given. Okay. Find the additional force required by the gyroscopic forces on the rails when the locomotive moves along a circle of radius something, velocity something. Okay, the gauge is equal to yeah, L equal to 1.5. The angular velocity of the turbine is given. What's the gauge? What is a gauge? What do you mean? Okay, this is just too complicated. I don't understand anything out of it. I can draw the thing in my head, so I'm gonna leave it. Yeah. Anybody else who understands what's going on, please, please eliminate me a bit. Fine. So I'll see you guys in the next video. And okay, bye.